So just to remind you from last time what we did, so we defined the discrete Gaussian free field on a graph G, and we gave three equivalent constructions of the discrete Gaussian free field. So the first construction, or the first description of it, was that we just described its the density of its law with respect to Lebesgue measure. And then we showed that this could also be constructed using a in terms of a series expansion with respect to an orthonormal basis of this Hilbert space that we had, H of G. And then finally, we showed that the discrete Gaussian free field can be described as a Gaussian vector which is indexed by the vertices in the graph where the covariance function is given by the Green's function for simple random walk on our graph. And then the last thing that we did last time is or second to last thing, is we established the Markov property for the discrete Gaussian free field. And today, what we're going to do is start a more or less parallel treatment of the continuum Gaussian free field. So this is our goal for today and next time. Is we're going to give a parallel treatment for the continuum Gaussian free field and we're going to be only interested in the case that this Gaussian free field lives on a domain in the complex plane. So we're going to look at the two-dimensional Gaussian free field. Before I go further, it was pointed out to me yesterday by Wendelin that he has actually been in the process of writing a set of notes on both the discrete Gaussian free field and the continuum free field, and also this notion of local sets that will come up a little bit later. And so if you want to take a look at his notes, he's just posted them online today on his website. So notes on these topics. This is a new set of notes which are still in progress by Wendelin Werner. These can be found just posted today on his website. So if you just search for his name, the very first link that you'll probably get will have a copy of these notes. Okay, so roughly speaking, what is the Gaussian free field? So the Gaussian free field H on a domain in the complex plane. This is it's the random Gaussian function with covariance given by the Green's function for the Laplacian. So with the covariance of the function at x and at y equal to g of xy, where this g is the Green's function for the Laplacian with Dirichlet boundary conditions on D. So in other words, this function g, one way to describe it is that it's characterized by the following two properties. Number one, if you take the Laplacian of g, then this is equal to minus 2 pi times the Dirac mass located at y. So this is the Dirac mass at y, and this Laplacian, let's say it's in the first variable. And secondly, g xy is equal to 0 if either x is in the boundary of the domain or y is in the boundary of the domain. Okay? So this is just the continuum analog of the characterization that I wrote down for the discrete Green's function last time. And there's a pretty explicit formula for this. So explicitly, you can write g of xy as being equal to minus the log of the distance between x and y. And then you subtract from it the function that I'm going to call g sub y hat of x. And what this second term is here is it's basically what you need to add to the log function in order to get zero boundary conditions. So here, this is given by the harmonic extension of the function which associates for each fixed value of y the log of minus the log of x minus y. And this is from the boundary of the domain to D. Okay. And this, again, this is just a correction that you add so that these boundary conditions here are respected. Okay, and if you look at this back up here to where I define the Gaussian free field, it's supposed to be a Gaussian function with this covariance, you see that there's kind of an obvious problem because what's supposed to describe the covariance function, this g, this has a log singularity, along the diagonal. So the variance of the Gaussian free field at any given point is infinity, and so it takes a little bit of work to make this precise. All right. Before going further, I want to point out one other thing. So there's kind of a nice complex analysis exercise that you can do at this point. And that's that if your domain D is simply connected, then it turns out that if you take this function I define g hat sub y and you evaluate it at y, this turns out to be equal to minus the log of what's called the conformal radius of y, or sorry, of your domain as seen from y. So here, let me just give the definition of this. So this this is the conformal radius of D as seen from Y. And let me remind you now what the definition of this is. So what this is this is equal to phi prime of 0, where phi is the unique conformal map which goes from the unit disk to your domain D with phi of y equal to 0, or sorry, phi of 0 equal to y, and phi prime of 0 positive. Okay, so this is just sort of a nice thing to think about if you have a chance. All right. So what I'm going to do now is give a construction of the Gaussian free field in terms of a series expansion, which is going to be analogous to the second construction that we gave last time for the discrete Gaussian free field. Okay, so we're going to construct the Gaussian free field using a series expansion. And in order to do this, we need to introduce the right space. And what is that space? So we need a continuum analog of the space h of g from last time. Okay. And so to define this, I need to define an inner product. So for functions f and g, which are, I'm going to assume that they're compactly supported in C infinity in D, I'm going to set their inner product to be equal to 1 over 2 pi times the integral over D of the gradient of f dotted with the gradient of g integrated against Lebesgue measure on my domain. So this is just the Dirichlet inner product. Okay, and this is just like the discrete Dirichlet inner product that we had last time. And the space that we're going to use to construct the Gaussian free field, I'm going to call it h of d. And this h of d is just the Hilbert space completion of the set of compactly supported C infinity functions with respect to this inner product that I just defined. Okay. And so finally, what is the Gaussian free field? The Gaussian free field, H on D, is given by the formula H is equal to the sum from n goes from 1 to infinity of alpha n times phi n, where here these alphas are a infinite sequence of IID normal 0, 1 random variables. And the phi's are an orthonormal basis of this space H of D. Okay. So far, this construction is pretty much, well, it's sort of exactly analogous to the construction of the discrete Gaussian free field that we gave last time. But one big difference is the following, and that's that if you calculate the norm of one of the partial sums in the series expansion, then what is this equal to? Well, it's just going to be the sum of the squares of the coefficients, so the sum of the squares of the alphas. And since these alphas here are just IID normal 0, 1 random variables, this goes to infinity as n goes to infinity almost surely. Okay, so there's this kind of annoying problem that the object that you're supposed to get when you take a limit of this series expansion does not converge in H of D. So this H that we're defining, this does not take values in the Hilbert space that we used to define it, H of D. Okay. And this, as I said, this is in contrast to the discrete case. So as we're going to see in a moment, what we're going to have to do in order to make sense of this is we're going to need to pass to a larger space than H of D in order to take the limit of the partial sums in the series expansion for H. Okay, and so this is kind of one of the little technicalities that makes working with the continuum Gaussian free field a bit more difficult than the discrete Gaussian free field. But before we go to that, I want to point something else out, and that's that that's the following. If I have another function f which is in H of D, and its series expansion looks like this. So it's the sum from n goes to 1 to infinity of an times phi n. Okay. Then I can try to compute the Dirichlet inner product of H with f and try to make sense of that. And if you calculate say that what should be the second moment of this, what is this? This is the same thing as the expectation of the sum of the product of the coefficients in the two series expansions. Well, this is going to be the same thing as the sum goes from n from 1 to infinity of an squared, just because the alpha n's are IID normal 0, 1. And in this summation here, this is going to be finite because this is exactly equal to the norm of f with respect to the Dirichlet inner product. So this is less than infinity. And because of this, we see that it actually does make sense to consider the Dirichlet inner product of the Gaussian free field with F. And it's also not hard to see that the distribution of this Dirichlet inner product is that of a normal random variable, and the mean is 0, and the variance is just the norm of f squared. Okay. So for a fixed choice of f in h of d, you can make sense of the Dirichlet inner product of the Gaussian free field with that function. And it's just going to be a normal random variable with variance given by the norm of the function. Okay, and moreover, if you have another function, g, in h of d, with series expansion given by the sum n goes from 1 to infinity of bn phi n, well, then we know that that g is going that the Dirichlet inner product of h with g, this is going to be a normal random variable with mean 0 and variance given by the norm of g squared, and we can calculate the covariance of the Dirichlet inner product that you get when you pair h with f and h with g. And what is this going to be equal to? Well, let's first calculate these two inner products here. So the first one is just going to be the product of the coefficients for h and f. So you get an alpha n. And the second one is just going to be the product of the coefficients of g of h and g. So you get bn alpha n. And again, using that the alphas are just IID normal 0, 1s, this is easy to compute. And you're just going to get the product of the a's and the b's. And that, of course, is the same thing as the Dirichlet inner product of f and g. Okay. So even though the Gaussian free field does not take values in h of d, if you have any function which is in h of d, you can make sense of its Dirichlet inner product with h. It's just going to be a Gaussian random variable whose variance is given by the square of the norm of your function. And you can also calculate the covariance of the Dirichlet inner product of h with f and h with g for any two functions. So that's very, very nice. But the kind of really annoying issue here is that for any fixed f, this Dirichlet inner product, this is only going to be defined up to a set of measure 0, which depends on f. Okay, and that's the very, very important thing here. Okay, so for any fixed function, you can make sense of the Dirichlet inner product of the Gaussian free field with that function, but this value is only going to be defined up to a set of measure 0, which depends on your particular choice of function. Okay. So in other words, the technical issue here is that the the Dirichlet inner product of H with F, this is not defined off a set of measure 0 which is common to all F. In H of D. Yep. Oh, just probability 0. So with respect to the probability space used to define the sequence of normals. Right, so what we're going to see in just a moment is that if we pass to a subspace of sufficiently regular functions, then you can get around this issue. But again, the difficulty here is that you can't just use the separability of the space H of D because this is not a continuous linear functional on H of D. So you can't try to define the Gaussian free field on a countable subset and then somehow use continuity to extend it everywhere. Okay, so what we're going to do now is we're going to see that that we can arrange something like this to be the case if we restrict our attention to a subset of sufficiently nice test functions. Okay, so that's the goal now, is to try to construct the Gaussian free, or try to identify a subspace of test functions so that we can construct what should be the integral of the Gaussian free field against all of these test functions simultaneously with probability 1. And in order to do this, it's going to be helpful right now to make a choice of the basis of H of D. And you'll see why in just a moment that there's one particular choice which is extremely handy to use. And in order to set this up, we need the following little fact, following sort of handy fact from functional analysis. And that's that we can find an orthonormal basis of L2 on our domain. So this is not H of D, but a different space, which consists of eigenvectors, which I will indicate as psi n, of the Laplacian on D. Okay. Okay, so, and here, the eigenvalues, the associated eigenvalues, so with associated eigenvalues lambda n, which tend to minus infinity as n goes to infinity. These are actually, they're all negative eigenvalues, lambda n. Okay. All right. And the reason that this is a good choice is we note that if we take phi n equal to minus the square root of 2 pi divided by the absolute value of lambda n times psi n, then this gives us an orthonormal basis of our original space h of d since, well, if you just calculate the inner product of, say, two of these functions, then, you know, what do you get? If I calculate the Dirichlet inner product of phi m and phi n, then if I do an integration by parts, I see that this is equal to phi m integrated against the Laplacian of phi n. But since phi n is an eigenvector of the Laplacian, this is equal to, well, so I just get lambda n times phi n. And in the end, you have minus lambda n divided by 2 pi times the integral of phi m phi n. And that's the same thing as minus lambda n over 2 pi times the L2 inner product of phi m and phi n. And so from this, it's not hard to see that the phi's that you get from the size in this way actually are orthonormal in h of d, and it's also not hard to see that these actually these also span. So let me give you just a concrete example of this now. So let's suppose, just for concreteness, that we've taken our domain just to be the unit square in the plane. Then in this case, you can take your eigenvectors of the Laplacian just to be 4 times the sine of 2 pi I x. This is a function of x and y. So 4 times the sine of 2 pi I x times the sine of 2 pi j y, where I and j are non-negative integers. Okay. Then these functions give an orthonormal basis of L2 on this domain. This is something that everybody remembers from when they first learned about Fourier series. And the eigenvalue, which is associated with psi ij, with psi ij is, you can just calculate it And you get that it's going to be minus 4 pi squared times I squared plus j squared. Okay, so you have a very nice basis of functions here, and you can calculate the eigenvalues of the Laplacian explicitly. And another thing that I want to emphasize now is that if you take the lambda ij's and you order them to be decreasing, so you order these guys to be decreasing, then it's not hard to see that if you take lambda n and you divide it by n and then send n to infinity, then this is just going to converge to a constant just a finite constant as n goes to infinity. You could even calculate what that constant is in this case because everything is so explicit. All right. And this last point that I've mentioned here is actually going to be very important for us in just a moment because it's a special case of a much more general fact. Namely the so-called Weyl asymptotics. So what this says more generally is if you have any bounded domain in the complex plane, and you have the eigenvalues, lambda n are the eigenvalues of the Laplacian, on your domain with Dirichlet boundary conditions. And ordered to be decreasing, then it's always true that lambda n over n converges as n goes to infinity to a constant which depends only on your domain. And this is going to be relevant for us because it tells us that the absolute value of lambda n is proportional to n. Okay, so that's the thing we're going to use in just a moment. All right, and this you can find in many places. So one place that you can find this, for example, is there's this undergraduate book on PDEs by Strauss. And also many other places. All right. So now what we're going to do is we're going to use this fact to define a class of spaces in which the Gaussian free field will take values. And this will allow us to identify a large class of functions against which we can integrate the Gaussian free field off a common set of measure 0. Okay, so now what we're going to do is try to build this space. So let's suppose that throughout that we have our functions phi n, and this is an orthonormal basis of L2 on our given domain, which consists of eigenvectors of the Laplacian with Dirichlet boundary conditions on D. Then what I want to do is I'm going to define a version of the fractional Laplacian by setting the minus Laplacian to the s power of a function f, where here f is the sum, f expressed in terms of this basis is just going to be the sum of beta n times phi n. And I'm going to define this fractional Laplacian to just be what you get if you take the coefficients for your function and then you scale each one by the corresponding eigenvalue to the s power. Okay? So this is kind of a natural way to define a fractional Laplacian from this perspective. Okay? So this is a fractional Laplacian. And the way you should think about this is that if, for example, s is equal to 1, then, well, this is just the Laplacian, so it's like taking two derivatives. And if s is equal to a half, then this is supposed to be kind of like the square root of the Laplacian, so it's sort of like taking one derivative of your function. Okay. And so let's use this now to define our spaces. So the way that we're going to do this is we're going to start off with an inner product, and we're going to take a Hilbert space completion again, like before. So we're going to let HSD be the Hilbert space completion of the C infinity functions, which are compactly supported in D, with respect to the inner product so the inner product of f and g, the HS inner product, is given by taking your two functions f and g and then applying to each one of them the Laplacian to the s over 2 power. Okay, so that's the space that we want to consider. And you'll see why this is kind of a nice space to consider in just a moment. Okay, let me point out one more thing now. And that's that if you have two functions, f and g, which are compactly supported in C infinity and D, then I can write the L2 inner product of these two functions in kind of a funny way. So first of all, I can write g as what you get when you apply the Laplacian to the s over 2th power, and then I'm going to invert it by applying the Laplacian to the minus s over 2th power. So those two things just cancel. And from the way that I defined this fractional Laplacian, it's clear that I can that it's self-adjoint, so that this is equal to minus the Laplacian to the minus s over 2th power applied to f paired with or integrated against the s over 2th power of the Laplacian applied to g. Okay. And now, if you apply the Cauchy-Schwarz inequality, you see that this is less than or equal to the norm associated with the HS inner product, where for f we have the minus s norm, and for g we take its HS norm. So this is just applying the Cauchy-Schwarz inequality. Okay. And the significance of this is that this tells us that we can think of a function, or an element, I should say, of h minus s as a continuous linear functional on HS, where the pairing is just given by integration. Okay. All right, and now finally, what we're going to do is we're going to show that you can think of the series expansion that we described for the Gaussian free field as converging in one of these H of S spaces. Okay, so let me state this result. So we want to think now of the Gaussian free field as a continuous linear functional. And the result says that if we fix any epsilon positive, and we let phi of n be an orthonormal basis of h of d, which consists of eigenvectors of the Laplacian, ordered to be non-decreasing, eigenvectors of the Laplacian with eigenvalues ordered to be non-decreasing and then we're also going to let alpha n be a sequence of IAD normal 0, 1s. Then the partial sums of the series expansion for the Gaussian free field, these converge almost surely in h minus epsilon. Okay? And upon showing this, we've now identified, an explicit class of functions with respect to which we can make sense of integration against the Gaussian free field almost surely off a common set of measures 0. All right, and in the last few minutes, let's give the proof of this. It's very short. So let me just remind you from earlier that we can write phi n as being equal to minus the square root of 2 pi over lambda n times psi n, where here these psi n's give an orthonormal basis of L2, and these are the same functions that we use to define the spaces H of S. Okay, and now what we're going to do is very simple. We're just going to calculate the the second moment of the H minus epsilon norm of these partial sums. Okay, so we're just going to calculate this expectation. Now, first of all, since these phi n's, the phi n's are going to be orthogonal in H minus epsilon, we can just expand, we can just switch the order of this norm and the summation. And we get the sum from n goes from 1 up to big N of alpha n squared times the norm of phi n H minus epsilon squared. Okay, so we didn't really do much there. And now, since these alpha n's, these are just IID normal 0, 1 random variables, if we take an expectation, these are just going to drop out, and we get the sum from n goes from 1 up to big N of phi n squared, or sorry, the H minus epsilon norm of phi n squared. And so to finish, we just need to calculate, we just need to actually just estimate what this norm is and show that this is going to give us a summable series. All right. So it's not hard to check that if you use just the definition of the H minus epsilon norm, and that these phi's come from eigenvectors of the Laplacian, that this sum is just going to be equal to the sum from n goes from 1 up to big N of lambda n to the minus 1 minus epsilon. Absolute value of lambda n to the minus 1 minus epsilon. So one can just do this short calculation. And then the Weyl asymptotics these tell us that the lambda n's are just proportional to n, so this whole thing is going to be less than or equal to some constant times the sum of n goes from 1 up to n of lambda n, or sorry, of n to the minus 1 minus epsilon. And this, of course, is finite because the exponent that I have for my n's is bigger than 1. So this is just going to be less than or equal to the sum of this whole series, and that's finite. Okay, and therefore the the second moment of these norms, H minus epsilon norms, are finite, and that implies that almost surely the series actually converge. Okay. Okay, and this tells us that we can make sense of the Gaussian free field as a continuous linear functional on h of s. Or sorry, h of epsilon for each positive value of epsilon. Okay, and using this, so using this proposition, if we have a function which is in h epsilon of d, for epsilon positive, we can define the L2 inner product of h and f to be equal to what you get when you apply the Laplacian to the minus epsilon over 2th power to h and integrate it against the Laplacian to the epsilon over 2th power applied to f. You take the L2 inner product of that. Because if this guy is in h minus, right, because if this guy is in, actually, sorry, I'm going to put just epsilon. If this guy's in h minus epsilon, then this inverse Laplacian will take you into L2, and if this guy is in h epsilon, then this Laplacian will take you into L2. So this makes sense to write down. And often, we'll kind of write this informally, although this makes even less sense, as the integral of h of x against f of x with respect to Lebesgue measure. Okay, so this is the most kind of informal statement because it doesn't really make sense to write down h of x when h is the Gaussian free field at a given point. All right, and so what are we going to do next? What we're going to do next is we are going to identify the covariance function like we did for the discrete Gaussian free field. Then we're going to show that the Gaussian free field is conformally invariant, just like Vincent showed today that Brownian motion is conformally invariant. So we'll establish conformal invariance. And then we're also going to take a look at the so-called circle average process for the Gaussian free field. Okay, and I think I'll stop there. Does anybody have any questions? Yeah.
So it's not a very well thought out question, but how much of a problem is it that there's not a canonical epsilon to use? Or is there canonical epsilon to?
It's not a big problem in general. Yeah, it's not a huge issue. There isn't really a canonical epsilon, but if you just often you could just restrict your class of test functions even just to be the C infinity functions. The most annoying issue is that you just can't take epsilon equal to 0, so you can't integrate against an L2 function. But it technically isn't that big of a deal when you actually prove things.
How general is the wild asymptotic, and is it true on manifolds?
Yeah, so I'm not a geometer, so I'm not the best person to answer this question. I mean, this is certainly true for if this is any subset of RD.
It's true for any manifold. I don't know what kind of restriction, but for very large class.
Right. Yeah, I think there's a whole other world where people look at the asymptotics of eigenvalues on compact manifolds and try to see what types of things you can tell about the manifold if you just see the eigenvalues. But that's not my specialty.
It's important that the domain be at least bounded, because otherwise you can't even you don't even have a countable number of eigenvalues.
Yeah, I mean, if you want to construct the Gaussian free field as a continuous linear functional this way, then it is important that the domain is bounded. However, if you just want to integrate it against, say, C infinity functions, then it's not a problem. Because one thing that you can do, for example, is you can first construct it this way in a bounded domain like the disk, and then you can apply a conformal transformation and take it to something unbounded. And as long as your function has compact support to begin with, then it will afterwards, and everything will be okay.
On the other hand, in high dimension, you cannot, like in dimension 3 or more, you cannot use this trick to define the Gaussian free field.
You can do exactly the same thing in higher dimensions. The difference is that the exponent that you get here is going to change.
No, but I mean if the domain is not bounded.
Ah, right. If the domain is not bounded, then you can't use conformal invariance anymore. But nevertheless, another trick that you can use is if you just restrict, you can try to construct what should be the restriction of the Gaussian free field to say a cube, and then you could use a construction like this, and this will work. And then once you've constructed it kind of on all cubes, then you've got an object, defined on your, say, unbounded set. And then once you have that, you can say at least integrate it against compactly supported test functions without a problem. Yeah.
How much does the construction depend on your choice of basis?
Oh, so the object that you're going to get is not going to depend on the basis. And essentially the reason is that if you remember from the beginning, the main thing is just what the covariance function is when you integrate the Gaussian free field against a test function with respect to the Dirac-Lie inner product. And from this construction, it's clear that what you're going to get is not going to depend on the basis. Any other questions?